And then we are already familiar with the concept of Euclidean distance, isn't it? So we've done a lot of stuff which we have used it to calculate the similarity. So it shouldn't be something new. Okay. Then we will, okay, so 3 people. So I think that should be enough. Okay. Then we will see the requirements of building a KNN in R. Okay. What you need to do, and then basically go on to build a model. All right. Okay. So like I explained the last time, we have classification models, and then we have regression models, basically. Okay. So we have, in terms of machine learning, we have unsupervised machine learning and also supervised machine learning. All right. So you are all aware that with unsupervised machine learning, it deals with unlabeled data. All right. We don't have any target in mind. We now want to see whether there are patterns or so in the data set. All right. Now, when it comes to supervised machine learning, we have a situation whereby there is a target in mind. All right. So we either want to predict that target. Okay. And when it comes to predicting of the outcome variable, that is under supervised machine learning. All right. It could be a categorical outcome or it could be a numerical outcome. All right. Okay. So I explained to you the last time that with numerical outcomes, normally we will use a regression. Okay, regression modeling. Okay. And then when it is categorical in terms of the outcome, then we use classification. Now, when you come under classification, there are so many models, okay, under classification. The last time we spoke about logistic regression, where you can use logistic regression to predict an outcome, which is categorical in nature. Okay. Another classification model, another popular classification model is the k-nearest neighbor. Okay. Well, I'll share my screen. All right, okay. Right, so I was talking about KNN and the fact that it is a classification model, okay? So what this model is about is that it tries to identify K records in the training data, which has, in terms of similarity, the one that is nearest to whatever you're looking for. And then it classifies that K as being classify it as being the instance of whatever object is nearest to the K. All right, okay. So here, it looks at a class of, it works by, I will use a typical example later on to show you how it uses a number of votes, okay? So you have so many objects, and then when you specify your K, okay, this is not the same as K-means, okay? This K we are talking about is different from K-means, okay? So don't confuse it with K-means. So when you specify your K, all right, K basically is the number of objects in a particular neighborhood, all right? So when it wants to do a classification, the number of objects in that particular neighborhood will do a vote. So the one with the largest vote, or the one with the majority of votes, will be classified as such. Okay, so let's say we have computers, we have laptops, we have phones. Okay, so let's say the people in the neighborhood, we have 5 laptops, we have 3 phones. So if they are to vote, then the people in the neighborhood, as an example, okay, then whatever object we are looking at will be classified as a laptop because they have the majority of the votes. Okay, all right. So another typical example. So in this instance, let's say within your training records, okay, we have a pig, we have a fowl, and then we have some ducks. Okay, so we want to compare it with our test record and then do the classification. Okay, so the idea here is to look at records that are similar to or near the record that we want to classify. All right, and then it is classified as such. Okay, so it looks at, what it normally does is that we look at the distance or similarity, okay, between the objects. Okay, so the one with the shortest distance, okay, you know by now that the one with the shortest distance is the one that is most similar, all right, okay, or very near to the object that we are looking at. Okay, so the one with the shortest distance is classified as such. Okay, so let's see. So basically, the closeness is determined by the Euclidean distance, which you are familiar with already. Okay? So if you're looking at the Euclidean distance between 2 items, okay, 2 items, okay, so it's the difference between them, and then you square, and then you find the square root, okay, of that. Okay. Any questions about the Euclidean distance? I don't think there is, but if there's any question. Okay, so let's see how this is applied. Okay, so let's say we have tomatoes. Okay, the sweetness of the tomatoes is 6. The crunchiness of the tomatoes is 4. Okay, let's say we've established this. Okay, and then we have a green bean with sweetness 3 and then crunchiness 7. So if we want to find the distance between green bean and tomatoes, basically, okay, it is, we take the sweetness of tomato and then deduct the sweetness of green bean from it. We squared the difference, okay, plus the crunchiness of tomatoes minus the crunchiness of green beans, and then we square that one too. We add them up and then we find the difference. We find the square root. That gives us the Euclidean distance. Okay. All right. So let's look at. So this is just the green bean. Let's look at other items as well. So let's assume these values are for other instances as well. So we have ingredients. So we want to predict whether the kind of ingredients that we have. Okay, so we have in our test data. Okay, so we have grape, we have green bean, we have nuts, we have orange. Okay, so you've been given information about the sweetness and then the crunchiness. Okay, we looked at green bean earlier on, that is 3 and 7, remember. Okay, so if you want to find the distance between each of the ingredients and tomatoes, okay, remember that the sweetness of tomato is 6, and then the crunchiness of tomato is 4, all right? Okay, so that's what we have here. So here, the distance between the grape, which has a sweetness of 8, sorry, and then crunchiness of 5. Okay, if you want to look at the distance between that and the tomatoes, remember tomatoes has 6 and 4. Right. Okay, so we deduct the crunchiness. In terms of crunchiness, we deduct that of the grape from tomatoes, which is 6 minus 8 squared, all right? Plus the crunchiness. The crunchiness of tomato is 4 minus that of grape, 5, and then we square that as well. That gives us a Euclidean distance of 2.2. So we've already calculated that for green bean, remember? Okay, so we do for nuts, we do for oranges. Okay, so out of the which one has the guys, please can you turn off your microphones? Okay, we'll be snappy today, so please, as much as possible, let the noise go down. So I'm asking, out of these 4, which one has which one is very close to tomatoes? Or which one is very similar to tomatoes? Grape, green bean, nuts, orange.
Orange.
Orange, why?
Shortest distance to tomatoes.
It has the shortest distance to tomatoes. Okay? It has the shortest distance to tomatoes. Therefore, in terms of this example, orange will be classified as tomatoes. Okay? So we use the one with the shortest distance and then we classify it as such. Okay. Let's look at another example how KNN can be applied. Let's take an example of a self-driving car. Okay, a self-driving car. So nobody is driving the car. So how does the car know when to stop? Okay, how does the car know when it has reached a pedestrian crossing and that it needs to yield? Where does the car determine that, okay, I'm not stopping, I'm not a pedestrian, I'm not at a pedestrian crossing, so I need to speed. And then which speed limit should I even use? Okay, so this is a typical example of, it's much more complicated than this, but the idea is the same. Okay, so if you have a self-driving car, there are sensors on the car. Okay, so when the sensors see the road signs, okay, it needs to be able to predict that this road sign stands for this. All right, if it stands for this, then it affects the behavior of the car, whether to stop, whether, so it depends upon the sensors or the feedback that the sensor is picking from the road signs. Okay, so let's say we have this. How can we apply a KNN? So let's say you have a car which has cameras and which can capture the road signs, and you are being asked as a data scientist, how can we use KNN to train the car? All right, to train the car in order for the car to know when to stop, when to determine whether it is as a pedestrian crossing or when to adjust its speed limit. Okay, so for example, you stop at intersections, you yield to pedestrians and adjust speed appropriately. Okay, So over time, as you instruct the car itself creates a database and then logs on to the sign. So as soon as it sees this sign, and now it has now learned that this sign means that stop. This sign means that, adjust your speed. This sign means that yield to pedestrians. Okay, so basically, it's one of the practical applications of ANN. Okay, now, in order for the car to determine to predict basically what the sign is, okay, it uses Euclidean distance. I'm going to send you a data set that is made out of road signs, okay, and then you will see, okay, for instance, that the road signs consist of different color intensities, okay? So you have color red, you have color green, color blue, okay? So the combination of the color intensities in the signs, okay, will let the car know, okay? Because the car will look at the sign and then be able to predict. Now, how does it do the prediction? It does the prediction by looking at the closeness of the colors or the signs. Okay, so let's say we have three main features here. Okay, so we have what we call a feature space. Okay, so the basic idea behind KNN is that all features that are close together are the same. Okay, so if you look at red, for instance, there are various color intensities for red. So you see that all signs that relate to stops will be together. Okay, they are the same. So when it sees stop here in, let's say in Accra, and it sees stop in Kumasi, for instance, because of the color intensity of the car, it's not looking at the physical distance, it's just looking at the color properties within the sign. It can determine that this means stop. Okay, now there are so many other various signs for pedestrian crossing. All right, now the idea is that all these things are clustered together, they are close to each other. Okay, so when it sees one, okay, it's able to predict that, okay, this one is for pedestrian, okay, due to the color intensity of that it's receiving from the sensors and so forth. Okay, so it uses Euclidean distance to judge all this. So the closer it is to a particular neighbor, then that item will be classified as part of those in that neighborhood. Okay, so if something is very close to, an item is very close to, let's say, stop, then it's most probable that it's part of the stop neighborhood. If it is very close to the pedestrian signs, then that item is classified as a pedestrian sign. Therefore, I'm probably at a zebra crossing, therefore I should stop. Okay. Any question? Any question? When we take some examples, I'm sure some of these things will come out clearer. But do you get the basic idea of ANN? Yes, yeah.
Yes, please.
Yeah, your
Nana,
hand is up. Yes.
yes, Nana. So with thinking about this and thinking about K-means, it seems it works similarly. Or can you a little bit juxtapose the two, how different they are?
Okay, so K means, the K is just the number of clusters. Okay, so the K means just tells you the number of clusters you have that you want to get. All right. Let me go a bit further. I will get to a particular slide. I think it will be better for you to understand. Okay.
Okay, sir. Okay, sir.
Okay. Now I'll get you the slide. Okay. So we will look at how we apply this in R. Okay. but it's very simple. The function is just KNN, okay? And then it takes three main arguments. It takes your train data, it takes your test data, and then your train labels, okay? I'll explain the train labels. Okay. So the letter K specifies the number of neighbors to consider when making a classification. Okay. So as I'm explaining this, you will see that it has a slight difference between this and then K. The letter K specifies the number of neighbors that you consider when making a classification. By default, R uses 1 for K. Okay, that is, it uses 1 neighbor. All right, you will see whether having small number of neighbors is good or bad. Okay, so here where the K is set as 1, it means that only one single neighbor is available. Okay, and that will be used to classify the unlabeled data. Okay, now see the situation, and then you see how this one differs from K. So K means you just give the you specify the number of classes ahead of time. Okay. But here, what we are doing is not really specifying the number of clusters, but we are looking at particular people in a neighborhood. Okay. So suppose our vehicle, that's the driverless vehicle, okay, or self-drive vehicle, okay. Suppose our vehicle observed the sign at the center in figure 2. So you see the pedestrian sign there, okay. It has 5 neighbors, isn't it? Okay, so at the top, we have 3 pedestrian signs, and then very close to it, there is a speed limit, and then far from it, another speed limit. Another speed limit. Okay, so we have 5 neighbors. Do you agree?
Yes, Nana.
Okay, so when we if we should set our K to 1, we'll go to R and then we set our K. But if we should set our K to 1, and then it works it out, the closest distance out of this in terms of Euclidean distance, the first one, speed limit 35, isn't it? Is the closest to the pedestrian, isn't it? So if you set your K as 1, will it correctly classify the sign?
No.
Would the car stop? Would the car will not stop? Okay.
It will reduce speed, but it won't stop.
Yes, it will adjust the speed by to not stop. Okay. Why? Because we set the neighbors to be only 1. So let's say we set the neighbors to be 3. Okay. If we set the neighbors to be 3, now we have the 2 other closest are number 2 and number 3, isn't it? They are all pedestrian signs. Did you get me? Okay. So now these 3 are the 3 in the neighborhood. So how does the KNN classify? It has 2 pedestrians and 1 speed limit. So they are going to vote. So the pedestrian signs are what? 3. And then the speed limit is 1. Therefore, it will classify it as pedestrian because it has the majority vote. Okay. Now, let's say we increase the neighbors to 4. That even makes it better, isn't it? Now we have 3 pedestrians and then 1 speed limit. Okay? So pedestrian wins again if we take a vote. So it will classify it as pedestrian. Okay? If we increase K to 5, now we have 5 neighbors. All right? We have 5 neighbors. What do you think the classification will be? We have 5 neighbors now. What do you think the classification will be? Anybody?
I think it will still be the pedestrian crossing.
Why?
Because you see that the three of them are still closest to the target than.
So they are all close. So they are all near. Some are very near. But if we said there are 5, you see that we have
if we
3
say there are 5, the
pedestrians.
speed
They are
limit.
the majority, isn't it? Therefore,
Yes,
it will
they are.
classify it as pedestrian.
Okay,
So
so the K is not about the number of
no, it's not about the number.
classifications, but
No,
just
it's
the
about the
neighbors
people in
it
the
will compare
neighborhood
with.
that helps it to classify exactly.
All right, makes sense.
You see the
Thank you.
difference? Yeah, you see the difference?
Yes, sir. I see it small.
Okay. Don't see it
Yeah.
small, see it big. Okay. But that said, okay. That said, so this one is so explaining what I just said. Okay. So if we increase the number to 2, we have 2 pedestrians. If we increase to 3, we have 3 pedestrians. If we increase the neighbors to 5, now it takes all of these together. But how is it going to classify? It's going to classify based upon the majority of the vote, which is pedestrian. Therefore, the car will stop. It will yield, it will think that it is at a zebra crossing, and therefore pedestrians are crossing. All right? Okay. Now, per our example, it was established that the higher the value of K, the better, isn't it? But it is not always like that. It is not always true that the bigger the K, the better. The smaller the K, sometimes the smaller the K, the better, because it is able to look at very subtle patterns. It can determine subtle patterns. Okay? However, if we go and make it bigger, okay, it will, what it does is that, especially if the bigness in quotes, okay, is as a result of noise. If it is as a result of noise, and then you make your K bigger, what it does is that it can misclassify. Okay, so if you see this, okay, you see that the ones below the dotted line has a circle, but that circle has been classified as a triangle or a diamond. Have you seen? So it is not always the case that you should set your K to be quite big. Okay? So which one do we go for? So what we do is that you try to optimize your K. Okay? We will see that when we go to R, we try to optimize your K. Okay? Now, in terms of K, even in the first place, how do you choose your K? The rule of thumb is that you look at your train data and then the number of observations in your train data, and then you find the square root of it. So let's say in your train data, you have, let's say, 100 observations. Find the square root of it, that is 10, and then use that for your K. That is just one instance, okay? Another one too is to look at various values of K, okay? And then compare it with the accuracy of the model. Okay, we've done accuracy, isn't it? When we did the confusion matrix, we did accuracy. All right. So you can choose, you can select some number of K and then see the effect it's going to have on the accuracy of the model. And then you choose the one that is optimal. That makes the model more effective. Okay. Any questions about how we select K and then basically what we've discussed so far? Any question? Any question? How we select K and any other issue? Any question? Yes, Francis.
Yes, Nana. So let me take you a little back. When we got to the classification with the highest number of observation, you get the result of the one being the highest. So my question is, if you can go to that slide. the one with the pedestrian walk and the
Yeah,
speed.
this one. Yeah.
Yes. So in the case where the observation, what the vehicle is looking at is the pedestrian in the middle, but then it has 2 speed limits and 1 pedestrian to compare with. Does it compare it with the highest, which is the speed limit?
No, it looks at the majority of the votes.
Yes. So we have 2 speed limit, 1 pedestrian.
You
So
have
we
2
have
speed
3.
limits. So
Yeah.
in that case, it's going to classify as speed limit.
Okay. Which is wrong.
And
How would you know
which
it's
is
wrong?
and which is wrong. So that will you look at, you see your accuracy, isn't it? You see when you do your confusion matrix, isn't it?
Okay.
So when you do your confusion matrix, the one that has been misclassified, you'll be able to detect.
Okay. All right.
Okay. And remember that the confusion matrix is always the comparison between your test data and then your predictions. All right?
Okay. Thank you.
Okay, Michael, yes.
And Nana, I wanted to find out that the K, does it select as random or it has a sequence that it selects from there?
Yeah, so that's what I just explained, that with the K, in selecting the K, you could use, there's no particular way of selecting the K. The main thing is that select something that makes the predictability of your model very effective. Okay. One way to select the K is to look at the number of instances or observations you have in your trained data set. Okay. So let's say you have 100 observations, find the square root of 100, and then it will be 10. Okay. So you can set your K at 10. Another alternative approach is that select a couple of K values. All right. And then see the effect that the K value is going to have on the accuracy of your model. Any K that you set, you'll be able to determine the confusion matrix of that K. Okay. And then based upon that, you'll be able to determine the accuracy of your model. So let's say if you choose, then we will do an exercise in R. Let's say if you choose K to be 1, what is the effect on the accuracy? Let's say the accuracy gives us 70%. Okay. We make K, let's say 5, the accuracy gives us 80%. Let's say we make K 8, the accuracy gives us 77%. So you go with the one with the highest accuracy. In this case, it will be 8. So you use 8 to build your model. This is okay.
And so Nana, what I'm saying is that if we should all choose 5 as our K, are we going to get the same accuracy or it's going to be different for all of us?
I don't get you. If we all choose 5 as our K. Yes, so we are going to have, yeah, so the accuracy basically will be the same. Just that if we are using, let's say, 1 laptop, okay? Okay. So the issue has to do with basically the number of the kind of should I say the kind of observations that you have in your trained data set. But it will not differ so much. So let's say we choose K, all of us choose K to be 5. If the accuracy is, let's say, 80%, all right, I work out to be 80%. It shouldn't be so much different from what you also get. You should also be getting something around 80%. If we all choose 5 and my accuracy is 80% and yours is 50%, there's something wrong. You get what I mean?
Oh, okay.
Okay. So we should all get a very good model. Okay. So that is why it's good to set your seed. Okay. Set your seed so that every time you run it, you get the same answer. So if per what I have, I set my seed and then I send it to you and you run the same thing, you get the same answer I'm getting on my laptop here. Okay.
Oh, okay.
All right. So yes. Yao, your hand is raised.
Yes, Nana. So Nana, please, pardon my ignorance here, but I was thinking about this. So when we're doing K-means, which was unsupervised, that we had the scree plots. That's the able thing to help us determine the optimum K for that.
Yeah.
In KNN, can we use a similar method to determine the optimum
Yes,
K
we can do a function to give us so basically with K means we're looking at the sum of squares within, and then the sum of squares, the total as compared to the total sum of squares. Okay, so
yes,
based upon that, it was rather using the error to the one with the least error to tell us that this will have the most this one will be most beneficial. It's not the same thing we are doing here. Okay, so the scree plot that we did was in terms of error. Okay, so the number of classes that will give you the least error. All right.
Okay.
All right. Okay, so let's quickly go into R and then see how we can apply this concept. Okay. All right. So let me send you this data set quickly. Just a minute. Please bear with me. Please, I will not keep you for long. So we will not go beyond 9 o'clock. Okay. So no break. Okay. But if you want to get something to drink, you can get it now. I'm loading my WhatsApp web. So if you want to get something to drink, you have about 2 minutes to do that. Download it and then bring it into our. Okay, so let me share my. Please, have you received it?
Yes, ma'am.
So just set my working directory. Let's call a couple of libraries. Have you used read R before? This one, read R. Have you used it before?
No, sir.
Okay, so install it. It's another way by which you can read your stuff. It's very easy. It makes manipulation of your data very easy. So install the packages read R. Okay. So, switch R. And for PNN, we need to install classification package. Okay, so we install the class package. Okay. Okay. So when you finish, then you call it from the library. Yeah. So call these three guys. I have it already, so I don't need it. So, okay, so you finish with the read R, and then I'll show you some slight differences between that. Read R is really fast, okay, as compared to base R commands. It's very fast, and then you can when it comes to data manipulation. So you can read on the documentation about read R. So normally you see that when we're, let's say, reading CSVs, okay, we have read.csv, okay. So this comes with the utils package, okay. So it's part of the base R, all right. When you use read R, normally you use read underscore CSV, okay. It's very fast, okay. So here we are reading an RDS file, so use read underscore RDS. Okay. Okay. All right. So here I think it was road science, isn't it? Road underscore science. RDS. So remember last week when we were using the base R, it was read RDS capital. Remember this one? But we are using read R. So just for you to, just in case if you see somewhere, you will not be, you will not say that, okay, you don't know what this is. So let's call this science. Okay, so let's view the data set. Now let's play. Okay, so if you see the data set, it has an ID column, then sample. So here it tells us which ones are the train, which ones are the test. Okay, that's how the data set was. Okay, then we have the sign type. Okay, that's if it is a pedestrian sign. Okay, these are the attributes of colors. Okay, these are the color intensities. So we have red one, green one, blue one, and then we have another color intensity, red 2, green 2, B2. Okay, so we have 16 properties, 16 different properties for red, blue, and then green. Okay, so for instance, if you take the first row like this, all of these properties combine together for us to have the pedestrian sign. Okay, all right. So there are other signs that tells it to adjust speed. All right. So these are the properties. Okay, color properties. All right. There are other signs that tells it to stop. Okay. So we will look at all that. Okay. There are a lot of them. Okay. So basically, that's what this data set is about. Okay. So here, let's go ahead and split. So here, the splitting will just do a filtering to filter the train from the test set. Okay. We will not use our normal splitting methods. Okay. But this one is given to us in the data set, so we can go by that. Yeah. Have we all imported the data set into our studio? Are we okay? Can we move on? Are we okay? Please.
Yes, ma'am.
Okay, thank you. So basically, let's have a glimpse of what we have. So let's have a glimpse of the science. I also have an overview of what we are dealing with. Okay, so all these color intensities are numerical values. Okay, and then we have the sign type. Okay, and then we have the ID and then the sample. Okay, so okay, so in terms of the sample, let's see, for instance, the sign type. Okay, let's see what the number of sign types we have here. Okay, we saw pedestrian and then speed. I didn't see stop, but I know it is there. Okay, so we can just check it from the table. Okay, so signs, and then we do a dollar sign. Okay, then we go to the sign type. Okay, that should. Okay, so it tells us that for pedestrian we have 65 observations, speed 70 observations, and then stop 71 observations. Okay. Okay, so let's go on straight to the splitting of the data. So here we are just filtering. Okay, so data partitioning. So we can just use a normal dplyr to filter our train data and then our test data. So basically, if you look at here, if you look at what we have here, the ID and then the sample columns, we don't really need them, do we? So this is just because this one is giving us the ID. We don't need the ID column. So we can just take it out. And then the sample column too, we don't need it. We will just filter and then take the train, separate the train from the test. After that, we don't need a sample column. All we need is the outcome variable, that is the sign type, and then the other predictors. Okay, so let's do that. So let's have our train data. Okay. All right, so we have our signs. Okay, let's pipe that. Another pipe operator is what we have here. So you can use the percentage greater than percentage or this, okay? Or this way, okay? It's another pipe operator. So let's filter. Let's filter and get our we'll get our tests, okay, and then our train, okay. So here sample. If you remember our dplyr, okay, you are interested in the train data. So train. Now, after we get it, we just want to get rid of the ID column and then the sample column, okay? So let's pipe this also. And we select. So we are not interested in the ID, so we deselect our ID. And then we deselect our sample. Yeah. Let's name this train data or sign train. What do you think? Or train sign? Train data. Okay. Let's run this. Okay, yeah, so this is fine. Let's get our test data. So basically the same thing. Let's copy and paste. Let's copy and paste this. We change this to tests. Okay, so this one, the filter changes to tests. Okay, and here too, we deselect the ID and then the sample, right? Let's run this. Good. Any question? Any question so far? Any question?
Nana, please. Are we using the symbol for the piping because of the packages we are using?
No. I just want to introduce you to it.
Oh, okay.
Okay. So you can use this or the percentage greater than percent. So just in case you see somewhere, you know that it's a pipe operator. Okay, so if you look at this, okay, are you seeing the slides?
Yes,
Yeah.
please.
The argument for the KNN, we see that it has the train data, test data, and then the train labels. Okay. When I was explaining, I said I when I was talking about this, I said I was explaining data. Okay, so the train data, you see the outcome variable. The outcome variable is basically the, for the train data is the train label. For the test data, the outcome variable will be test label. Okay, now, KNN deals with numerical values. All right, it deals with numerical values. So when we are inputting it into the function, okay, we separate the labels from the train data. So if, for instance, we are using train data, okay, what we'll do is that we will remove the outcome variable column, and then that will become our label. Okay, so that's how it is. So unlike logistic regression, where everything was there, here you remove that label and then come and put it under, remove that column and then come and put it under labels. Okay, and then we run the algorithm. Okay, so let's do that. So now, if you look at the train data, let's look at this. Let's run the train data. Let's look at a few lines. So if you look at the train data, you see that we have the sign type, okay? And then the, you see the other attributes, okay? So you see here, you see one of the advantages of using readr, it classifies the thing for you, okay, without you even going to look for it, okay? So I'll chip in some of these things as we go along, right? Okay, so it does, you see the sign type, it has the pedestrian, okay, and then it has the other numerical values, okay? So what we want to do is that we want to take off this, the sign type column, and that will come under our labels, okay? All right, so let's do that. So let's create our labels, create our train labels. So it's very simple. So we have our train data, okay? Our train data is this, isn't it? So you do the $sign, and then you pick the sign type. So that gives you the column. All right? So all that we need to say is that this one is our train label. Okay? So train labels. So we name it as train labels. So every time we call train labels, what we actually call them is the train data sign type column, right? So let's run this. Okay, so we have created our labels. So in fact, if you run it, it will only give you the outcome variable column. Okay, if you run it, have a look. Okay, it just tells you stop, or speed, or pedestrian. That's all, right? So now let's go and predict using our KNN. So we predict using KNN. All right. So it's very simple. So we use the KNN function. Okay. So the main idea is that the prediction, okay, is KNN, okay, and then it takes the argument for the train data or the train set, okay, So basically the train data, okay? And then the test data, okay? And then it takes the train labels, all right? So we've created all this. We have our test set, we have our train data, and then we also have our train label. So we can do our KNN. Okay, so let's do the KNN. So KNN, let's take our train data. So the argument train, okay, is equal to our train data, isn't it? Our train data. But remember that our train data, our train data still has the pedestrian, the sign type there. Okay. If you run this, where do we have our train data? This one. Our train data still has the sign type there. Okay. Now we have labeled this separately under the labels. So now if we are doing the train data, we should remove the sign type column. All right. So that is our first column. Okay, so let's remove that. So if you take the train data, okay, you just find use the square bracket to create a subset. Okay, so you use -1. That means that it will remove the first column. All right, it removes the first column of the train data set. Let's come to the test. So the test data too is the same thing. So here, the test is equal to test data. Test data, okay? And then we remove the first column. The first column is the sign type, isn't it? For the test data. So let's remove that as well. Okay. And then the classification argument, CL, is equal to train labels. Okay. Okay. Any issue with the syntax? Okay. And then let's name it sign predictions. Okay. So let's run this. Okay, so now we want to compare our predicted sign type to the actual sign type. Okay, so this is our prediction. Okay, so when we run this, you will see our predicted sign type. If you run this now, so this is our predicted, okay, using KNN. So let's compare it with the actual sign type so that we'll be able to develop our confusion matrix. Yeah. So if we want to see the number of pedestrians, the number of, you can just use the table to check the predictions. Yeah. So this gives you, so we predicted 21 observations for pedestrian, 17 for speed, and then 21 for stop. Yeah. Let's filter to get the actual test values. Okay. So our actual test values will come from our test data, isn't it? So we take our test data, okay? And then we go to the $, and then we take the first first column as a sign type. Okay. So let's name this science actual. Okay. Okay, so this one is coming from our test set. Okay. So now let's create a confusion matrix between our predicted and then the actual values. Predicted values. Now, when we were doing tidy models, everything we did with regards to the confusion matrix was within that ecosystem. Okay. Now we are not using tidy models here. R has several ways of calculating confusion matrix. Okay. So let's see one of the ways by which we can use to calculate it. Okay. Can use this normal table command to help us do that. So here, let's use a table function, and then we compare our science predicted with our science actual. Science actual. Okay. Run this. Okay. This is quite new. We are having a multi-class confusion matrix. What we've done so far is normal confusion matrix, which is it's not multi-class, it's normally binary. But here we have multi-class confusion matrix. So how do we go about this? Okay. Please, are we all here? Have we all gotten to this level where I am? Are we okay? Can I get some feedback, please?
Yes, sir.
Yes.
Okay. All right. So how do we go about this multi-class? So let me make a comment here. So this is a multi-class confusion matrix. So one way to go about this is, first of all, we need to determine the true positive. So the true positive is equal to where you have the diagonal, okay? So pedestrian is true positive. Speed is 17, that is true positive. And then stop 19 is true positive, okay? So the true positive is the diagonal. Whenever you have a multi-class confusion matrix, the true positive is the diagonal, okay, of the matrix. All right. So here we have 19 plus 17 plus what? 19, giving us a total of what? Can somebody help us? I want us to do it manually, and then we do it and compare our answer with R, so that whenever you meet it somewhere, okay, you meet a multi.
55.
Okay, 55. Okay. So now the false positive. The false positive, okay, basically is the sum of all values in corresponding columns except the true positive. Okay, so false positive is sum of all values in columns. Okay, except the true positive. So what this means is that if we take the first column, this one, the first one, 1900, 19 is part of the true positive, so we don't count it. Okay? So here, the false positive will be, for the first column will be 0 plus 0, isn't it? 0 plus 0. All right? And then the second column will be what?
Please, sir.
Yes.
2 plus 2.
Please, can you repeat the false positive for me?
So the false positive is, I've written it here. The false positive is sum of all columns, okay? Sum of all columns except, okay, let me make it sum of all corresponding columns. Corresponding columns except true positive, all right? So for the first column, 19 was part of the true positive, okay? So we don't count that. So we count the first one is 0 plus 0. What about the second one? Someone mentioned it.
2 plus 2.
2 plus 2. Okay. And then the last one.
0 plus 0.
0 plus 0. Please, does it make sense? Okay. So the true positive here will be 4. False positive will be 4. Okay. Yes. Our false positive will be 4. Now, let's check our false negative. So our false negative is sum of all corresponding rows except the true positive. Okay? So let me copy this. Sum of all corresponding rows except true positive. So this one is rows. Sum of all corresponding rows except true positive. So that one too. So this one we are looking at rows. So the first one, what will it be? The first row. What is the false negative?
2 plus 0.
2 plus 0. And then the second row.
0 plus 0.
0
0
plus 0.
0.
And then the last row.
0 plus 2.
0 plus 2.
0 plus 2. Good. Good. So this one is 0 plus 2. Yeah? That also gives us 4. Okay. What about a true negative? True negative for multi-class is always 0. Okay. So now, how do we calculate accuracy? We know that accuracy is true positive, isn't it? True positive plus true negative, isn't it? Divided by everything. Is that not so? So if we want to calculate accuracy here will be 55. That is true positive, isn't it? True positive of 55 plus true negative of 0. Okay? Divided by everything. What is everything? That means we add 4. This plus what does it give you? Oh, divided by everything. Okay. So what I mean by everything is that here, if you add how do you call it? If you add everything in the matrix, okay, what does it give you?
59.
59. Okay. So that gives you 55 divided by 59. And that gives you what? So we are doing this manually, and then I will do it for us, but I wanted to take you through so that you know how it is.
0.93.
0.93. Okay. Good. So let's do it with R. So let's do it with R. So computing accuracy with R. So this one is computing accuracy manually. Okay. Okay. But this one we are doing it in R. Okay, so here we just use the mean. Okay, is the sign for the prediction, sign spread. Okay, that's the syntax. Double equal to, okay, signs actual. Okay, when you run it, okay, gives you exactly the same thing. Okay. There are so many ways of calculating the confusion matrix. If we use caret too, there's a way to calculate it. As we do other stuff, I will show you how to go about it. But this is one of the ways to calculate accuracy. Okay. Accuracy. Okay. Okay. So let's quickly see our values. Okay. By default, I told you that by default, R uses K is equal to 1. Okay. So that is the default. So let's compute the accuracy of the baseline model where K is equal to 1. Okay. Baseline model, okay? So where the default K is equal to 1. Where the default K is equal to 1. Yeah. So here, oh, sorry. So let me go and take my KNN. Where is it? We have our KNN here.
Hello, Nana.
Yes. Please go ahead.
Hello. Please, with the formula, the accuracy.
Yes.
Please, when we say everything, are we saying this thing, the true positive plus the false positive plus the false negative?
If you do it like that, you make it 8. So no double count. Okay. So just
okay.
Because if you don't take that, you double count and then you don't get the 15. I was expecting somebody to ask this, so well done. Okay, it's very easy to add 4 plus 4 and it becomes 8, and then you add it to 55. That gives you 63, isn't it? Okay. So here, let's see. So here, because it's a default, you don't really need to show it, okay? But actually what is happening here is that K is equal to 1. Okay, K is equal to 1. So that's it. So let's name this K is equal to 1. K underscore 1, for instance. So here K is 1. Therefore, this is our Okay, so if that is the case, let's find the accuracy. If you find the accuracy, okay, here so we have the actuals, okay, K1, okay, so that is the predicted, okay, whichever way you do it, it will give you. So let's check the accuracy. So here the accuracy is 93%. Okay, let's modify it and then change K to 7. So it has 7 neighbors. Okay, so modify and set K is equal to 7. So here, now we have 7 members in the neighborhood. Okay, so let's just copy this. So let's change this to K7. Yeah. So now it's no more the default. So we need to specify the K. Okay. We need to specify the K. So here there's an argument called K. K is equal to 7. All right. So we run this. Okay, and then we find the accuracy. So here too, let's find the accuracy where K is equal to 7. So here K is equal to 7. Let's find the accuracy. So here the accuracy is approximately 95%. Okay. Let's set K at 15, for instance, and then see. So modify and set K at 15. Okay, so now we change K to 15 here. And then here too is 15. And then our accuracy, we change K to 15. Let's run it. Let's see. Okay. Let's check our accuracy. You see that so it has reduced to 88. So the fact that K is larger doesn't necessarily mean that it's the best. So here in this scenario, you see that K7 is the optimum. Okay, so we use K7 to build our model. Okay. Let's use K7 to build our model. Let's use K is equal to 7. Yeah. So let's view modifications. Let's copy this. Now we want to see, after we build our model, we want to see how they voted. Okay. So this is what we are using to build our model. So let's name this sign predict. We'll make this sign predict 2. Okay. Let's make this A is equal to 7. And now our probabilities argument, let's set it to true. It will tell us how they voted. Okay. Let's run this. So these are our predictions. Our predictions are here. Okay. Right. So let's see. So let's take our sign predictions, okay, and then see how the voting went. Okay. So what you do is you use the attribute function, okay, and then we apply it on the sign prediction. Okay. Add the Let's call this sign probability. Okay. Still caveat. So let's examine the first few predictions, okay? First data, we remove this. So let's examine first few lines. Yeah. So here we have, so our predictions, we have pedestrian, stop, pedestrian, and so forth. Okay. Okay. Let's look at, so we have the probabilities and also the predictions. Let's see how the voting went. Okay. So let's examine the proportion of votes for the winning class. Okay. So let's take our sign prediction. We'll say and sign. Let's see. Hello, can you hear me?
Yes, please.
Yes.
But you can't see your screen.
Yeah, just a minute. Just give me some few more minutes, okay? I really need to finish this, so that you can put this behind you. Right. So let me explain this. So what I've done is that, or what we've done is that we've combined the probabilities of the votings and then the predictions. So what this tells you is that 57%, okay, of the people voted. So there were 57 people in terms of people in the neighborhood, okay? Those who won, okay, they won by 57%. That's how come it was predicted to be pedestrian, okay? The second one, to those who won, was 57%. Here, to those who won were approximately 86%, okay? So that's how you interpret it. Okay, so this one gives you an idea as to how the voting went. All right? Okay, which means there were other alternatives, but these people were the majority. Pedestrian, so here pedestrian was majority. Here it was predicted stop, okay, because the stop were the majority of 57% and so forth. So you can have a look at all of them, all of the predictions, and see how the voting went. Okay, any questions about this? Let's quickly deal with some two more issues and then we are done. Yes, any question? Yes, please go ahead.
Then when I ran mine, I didn't get any negative. It was all positive.
You didn't get what?
It only predicted pedestrian and then speed.
It predicted only pedestrian and speed.
Yes, so
Okay.
you see your confusion between
check your table. Check this. Check your table. Use the table. Okay. Use the table to find out the sign type. Okay. For your predictions, use this syntax. Check the number of predictions that you have. It will give you for each of the classes. Okay. Please, any other question? Okay. Is it better now?
Yes.
Okay, good. All right. So let me come on here. How do we prepare our data? How do we prepare our data for KNN? Okay. Talking about all this. How do we prepare our data for KNN? Okay. Remember that KNN basically uses numerical data. Okay. So where sometimes you can have in your predictors categorical variables. Okay. So in doing that, let's say now we use the color intensity to, and then values were given to it. All right. What about if a sign is a triangle or a sign is a rectangle? Okay. How does it really differentiate, okay, between the two? Because that one you cannot give it a number. That's when dummy encoding comes in. We did it last week. All right. So with dummy encoding, you know that it's different from one hot encoding. So everything is changed to zeros and ones. Okay. However, we save space. Okay. Remember the example I gave you about finance department, marketing department, and then IT department. Okay. So if you have, let's say, a three-dimensional information, okay? So if it is not marketing, if marketing is 0 and then IT department is 0, then it is finance department. Remember the example that I gave. It's the same thing here. All right. So when you have categorical variables, we need to dummy encode it. Okay, you need to dummy encode it, and that changes it to zeros and ones. Okay, so it's what it does is that it converts all the categorical variables into numerical variables. Okay, so that you can do your prediction, and you can use your tidy models step dummy to do that easily. All right. Okay. And another thing too is normalization. Last week too, when we're doing feature engineering, we spoke about normalization. Okay. Remember that if you look at the data set, okay, the color intensity ranges from 0 to 255. Okay, if you check the summary of the data we have. All right. And let's go to our what we have here. Let's view the signs. Let's see summary of the signs. Okay. So you see that the highest here, the maximum is 243. Okay. And the lowest is 2. There are some that are 244. Okay. Here we are seeing 255. So they range between 0 to 255, basically. All right. The range between 0 to 255. But you see, the difficulty is that if you don't normalize, okay, let's say if we bring on the dummy encoding, okay, which is 0s and 1, okay, so if something is, let's say it's a rectangle, it's 1, if it is a diamond, is 0. So the difference between this 0 and 1 will be like this. However, in terms of color intensity, is 1 unit. Okay, changing from 0 to 255. So you see that speed limit, though it is nearer the pedestrian, it should be closer to these two guys here, okay? Because they are close neighbors, okay? But because of the color intensity, if we are to use the same variables, okay? It creates this as if the 35, the topmost 35 is far away from these two guys down here, the speed limit, 35 and 45 down here, okay? So when we do the normalization, and then everything is between 0s and 1, you see that it compresses it. So it's no more the one on the left. You see the one on the right, it has compressed it, and then you see that the 35 at the top is nearer to those at the bottom. So everything is between 0s and 1. It gives you a very comparable view of what is actually happening. All right. So you need to dummy encode your variables, and then you also need to normalize them. So normally what you do is that you can do all these things, and then when you finish, you do your data partitioning, and then you apply your KNN algorithm. Yes, yeah. Are you asking a question?
Yes, no. So although we have this data to be in numerical form, I thought when they are in numerical form, you don't do dummy encoding, but we can do the normalization to reduce the numbers and scale them. Why do we have
dummy encoding? You don't do dummy encoding for numerical values. You do dummy encoding for categorical values. Here in this data set, we don't have nominal predictors. The only nominal predictor we have was the outcome variable. Sorry, the nominal variable we had, okay, was the outcome, but we didn't have predictors that were nominal. I'm only bringing your attention to it that if you get a data set that has nominal predictors, okay. In this case, let's say rectangle and the diamond. It wasn't in the data set. But let's say if you get something like this, then you need to dummy encode. Have you seen?
Okay, understood.
Is it better now? Okay.
Yes, sir.
Good. Please, any other questions? So you do your dummy, and we've done it already, so I'm not going to go through this. Okay, so you do your dummy encoding. So these are preparations before you do KNN. You do your dummy encoding, you do your normalization, and then everything else that we've done today, you do it, and then you can be able to predict. Okay. All right. Any other questions?
No, one more question.
Okay, yeah.
On the results for the probability, if I'll take you back a little, what we are trying to predict, since we had train and test data, we're trying to see how each of the colors that we have, the 16 colors, how they were each trying to predict the test data. Is that the probability for each of the train data predicting the test data?
The probability you have there, the probability you have there is the voting, how the voting went. So that's how you interpret that one. It's how the voting went. So if you have a probability of 57%, it tells you that the pedestrian items in the neighborhood were 57% more than the others. So which means there were other signs there, but they made up 43% of the vote. So it didn't classify it as top. Okay, so you could have had, let's say, stop to be 23%, and then what's the other one? Speed to be, let's say, so everything should be 100. All right, you had pedestrian being 57%, and then you could have, let's say, the other one being, let's say, 30%, and the rest being 20%. All right, but so because the majority of the vote was 57%, okay, of pedestrians, it predicted it to be pedestrian. All right.
Okay.
It's if you remember, it's the same thing that we did here. This, if you remember, here, when we had this guy here in the middle here. All right.
Nana, please, I'll show you something. I'm not seeing your screen.
Oh, okay, I'm not sharing it. Okay, just a minute. I was sharing my slide. Okay. Remember this one. It's the same thing here.
Oh, okay. Okay.
Okay, so here 3:2. Okay, so it's going to be, what will be the probability here? 3:2.
Yeah.
So that is the probability basically. Okay. So here will it be this one will be 60-40, isn't it? Basically 60-40. Okay, so here the probability for the pedestrian will show 0.6, while the other one shows 0.4. Okay, so you don't see the 0.4, but you see the majority vote. All right?
Okay. Okay, sir.
Okay, guys, any other questions? So just go through what we've done. Okay, if you have any issues, we can discuss it on Saturday. Okay. All right. It's late already, so I will leave you. I will be here for the next 5 minutes. If anybody has anything to ask, you can do that. But thank you so much for making time to attend this evening. I will see you on Saturday. Okay, God willing. So I'll be here for the next 5 minutes. If anything or any other comments you want us to talk about, I can do that. So we are done. Thank you very much. So I'm here for the next 5 minutes. Anybody, any question? I will send you the slides and then our scripts. Okay. Any questions?
No, this is just for my curiosity. This, yeah.
Yeah, yes, yeah.
Yeah, kindly go back a little step, some few steps on the slides. I want us to talk about the traffic signs.
Okay, yeah.
Yes. So
Okay.
here you earlier mentioned that first of all, we needed to group them, cluster the signs into various groups before we apply the KNN to it for the.
No, no, you don't do any clustering. You don't do any clustering. So this one, the idea behind KNN is that variables that are close to each other are very similar. All right.
Okay.
So if you look at the speed signs, for instance, though there are 25, you have 25, 45, 35. Okay. The background and everything, they are very, very similar. So if it sees 25 in Kumasi as a road sign, okay, it knows that this is speed limit adjust to 25. If it sees the same thing in Accra, it will know that it is 25. Okay. Now, if the color intensity should change a bit, okay, that which makes it 45, then it will also take that it will also recognize that. All right. So you see that because these are very similar, they are very close together. Okay.
Okay.
Unlike, so if you take the speed limit and then the stop signs, they are not close to each other as compared to the ones for the stop signs. So we have various stop signs. So when you take the stop signs on their own, they are very close. They are all in the same neighborhood. Okay. If you take the pedestrian, there might be various type of pedestrian, signs, but they are very similar. Okay. So that is the whole idea behind KNN.
Okay.
So you read through and then if there are any other issues, you can deal with it.
Okay, no, thank you.
Okay. Have a blessed evening. Okay, guys. So thank you very much, and I'll send you the information very soon. All the best. Thank you. Bye.
Thank you, Nana.
Bye-bye.
Bye, Nancy.